Alright, we're gonna um, do the lecture on equilibrium. Actually, I'm gonna combine rates with equilibrium. Alright. And for short, equilibrium will be EQB for short, okay? And I'm gonna combine these two because they work well with each other. So first we'll talk about rates, okay? And in rates, usually we want to see, it means, it's a rate, so something that happens over time. And usually, and always we're talking about the amount, okay, the amount. So the amount, which, we know what an amount means. It's usually an amount of a reactant or product / product. Okay? And so to make things easy, we'll just assume we have some reactant A going to reactant B, or product B. Remember, products are on the right hand side of the arrow, reactants are on the left side of the arrow. Reactant A goes to reactant B. That's how we say this. Again, we want to see how these amounts change over time, and usually we can see this graphically. This is time on the horizontal, and on the vertical it is the amount. Initially we have reactants, okay? Initially there are a lot of reactants, right? So maybe this is my container and I have a bunch of reactants A initially at time t equals 0 seconds. 0 would be here. We have some amount of A, okay? So some amount, so I'll just put it up here. And as time goes on, the reaction starts. You start to form B, okay? Eventually, if you wait long enough until the reaction is complete, okay, you have only B remaining, okay? That is because all the reactant A has been converted to B. So, there are no more A's. So somehow we'll end up down here. It turns out that it will have this behavior, okay? So this is A, has some initial amount, and then it starts to decrease over time. Okay? So the amount of A decreases over time. Now, we also need to monitor B as time progresses. So initially, there are no B's. As you can see, there are no B's here. And so, graphically, we should see this behavior. Once it reaches this point, where there are no more A's, no more B can remain, okay? So this is now B, the curve B. And this is how we've been learning chemistry for the most part. We've been learning how some reactants can become products over time. Usually there are more reactants and usually there are more products, but I'm trying to make this simple. If there were more reactants, I would have to monitor those too. And if there were more products, I would have to monitor those also. So let's just make it simple like this. Okay, now we need to know what is a faster rate and what is a slower rate. Okay, so let's talk about A going to B. Okay, if it's slow, let's put slow, versus, we'll call this A prime going to B prime. It's the same reaction, A goes to B, but it's faster. It can be faster because I might change the temperature or something like that. And in this case here, I'm going to monitor the amount of B, okay? Amount. Okay, and B. So this is the amount of B forming, okay? We're going to look at the slow version and the fast version. As you know here, every time A disappears, B appears, right? Because if A disappears, it has become B, alright? In other words, if B appears, then that must mean one A has disappeared, okay? That's the stoichiometry we've learned. One of these to one of these. Every time one of these disappears, one of these appears. Okay, so now we're going to monitor B forming. The slow version would be this. The amount to B here versus time. Okay, just like this one over here, this curve over here. And what I'm going to say here is that we're going to first watch the slow version, okay? It takes a long time for it to completely finish. Alright? Whereas, so this would be slow, so this would be B, okay? Alright, and then B prime, if we're looking at the fast version, it would take a fast time. Boom, it finishes right there. So this one's much faster, this is B prime, which is the fast scenario, okay? And let's just make this B on the vertical, or the amount on the vertical. Watching the fast version, it's a lot faster relative to the slow one, right? It takes a long time to be complete. We're monitoring a product forming, or actually, I take this back. We're watching a reactant disappear, actually. So let me erase this. We're watching A slowly disappear. Alright, it takes a long time to completely disappear, and then we're watching A prime disappear quickly, okay? Because A is a reactant that disappears over time. Now let's look at the B version, which I should have talked about, I was talking about earlier. Anyways, amount and time here, and we're looking at B form over time. Okay, now of course the slow version is going to be, takes a long time, and then it finally levels off. Okay, so this is B taking a long time to complete. Okay, so that would be just regular B, okay? And then B prime would be much faster. It reaches that point a lot faster, so this is faster. Okay, so this is B prime here. Alright, so then you guys can get the idea of something going slower and something happening faster. Alright, and then we need to know, in rates, we need to know what affects the rate of reaction. What makes a reaction faster? How do we make something slow become something faster? And so those are the 5 factors. 5 factors. There are 5 factors that affect the rate, and I'm just going to list them all out here. So first, it is the surface area of a solid reactant. Solid reactant. Okay? If you increase surface area, we can call it SA, surface area. For solid reactants, if you increase the surface area, then the rate increases. Okay, the rate increases. The rate of a reaction increases. Okay, it's a faster rate. More products can form over time in a short amount of time. Okay, so an example would be like if you have like a big block of solid calcium, okay, and you have it in a container with excess amounts of oxygen gas, O2 gas, okay, and these O2 gas particles have to collide with the surface sites of calcium. Okay, this is a solid piece of metal. Okay, so it's big, you can see it, meaning that there's a lot of surface sites or surface atoms that O2 can collide with. Okay, so many surface sites. For collisions, right? Reactant collisions. Okay, the surface sites are exposed to the oxygen gas, so they are surface sites. So they are reactant sites. Okay, reactant sites. And then so oxygen gas, which is a gas, and they're moving in random motion very fast. It's a gas, right? So then every time an O2 gas particle collides with a surface site, then you could have a reaction, okay? Now, if you increase the surface area, you have more surface sites. Okay, so for example, now in this container, we're going to cut this piece of calcium into 2 blocks. It's the same amount of calcium, okay? It's just I've cut this one in half now. So now we have 2 pieces of calcium. They have the same mass though, so it's the same amount of calcium. Now you have your bunch of gas particles in here. And now you have a whole new exposed area for collisions to occur because you've increased the number of surface sites. Alright? And so now the gas particles can hit this surface, this surface, this surface, whereas over here it can only hit the sides of the cubes here. Now you have two rectangular cubes here now, so it has more surface sites to collide with. So that rate of reaction should increase here, okay? In other words, in this reaction, which would be calcium reacts with oxygen gas, goes to calcium oxide, and we could balance this like this, okay? Solid calcium reacts with oxygen gas to make calcium oxide, solid calcium oxide right here, okay? Alright, and so the amount of CaO forming here is a lot faster than over here. And you get the idea, we can even make it more exaggerated. If you have a condition where you have powdered calcium, solid calcium here. And then so if you have a powder, they react faster, okay? And you guys can remember this because a lot of times when we cook, we want a reaction to go faster, or we want to heat up our food faster so we can cut it into smaller pieces. That's because now there's more surface area that can be exposed to the heat, in turn cooking it faster. Or in this case here, more surface area of a solid reactant causes the rate of reaction to increase because there are more exposed surface sites. And then of course, if there are more surface sites for collisions to occur, then we can expect the frequency of collisions to increase. Frequency of collisions increase. Frequency just means some time, right? So frequency, the number of collisions per second. Okay? It's going to happen more here. So surface area of solids. If you increase the surface area of a solid reactant in some chemical reaction like this, the rate of reaction increases because there are more surface sites. More surface sites means that there's more collision frequencies, okay? And of course there are more frequency of collisions between reactant particles, okay? In this case here, the solid calcium and the oxygen gas, okay? So the collisions are between reactants. Alright, between reactants. Alright, so that's 1, okay? So let's go ahead and erase this. Now, sometimes reactants are gas particles, okay? So let's just say A gas, some reactant species A, that's a gas, reacts with some reactant species B, that's a gas, to form whatever, some product C. And we can assume that could be a gas too, no problem. In this case here, what we can have is, let's imagine gas particles A and B are added together in some balloon, okay? And I use a balloon because balloons are easy for us to visualize what's happening. In this case here, what we could do is we could increase the pressure of gas reactants, okay? This only applies for gas reactants because you cannot really increase the pressure of solids reactants or liquid reactants, okay, or aqueous reactants. aqueous reactants are inside of water, so it's hard to increase the pressure of those things, of those reactants. In this case here, they are gases, so I can increase the pressure. I can increase the pressure by squeezing the balloon, right? So if I squeeze the balloon, I decrease the volume that it's in, and this increases the pressure. Okay? If I increase the pressure by doing this, what you will see is there's less space between particles. Okay? All right, so less space between particles, reactant particles. All right, what does this mean? This means that there's more likely to have more collisions, okay? Because these things are moving around, bouncing off of the walls and hitting each other, okay? So the frequency of collisions also increase. And again, this is frequency of collisions between reactant particles, okay? All right, now this was the same case with increasing the surface area of solid reactants, okay? Because you know, if you increase the surface area, there are more surface sites for collisions to occur on. Also increasing the frequency of collisions, okay? All right, so this has to do with pressure. Okay, so this is number 2. All right. The next part has to do with concentration, okay? Concentration. It's kind of very similar to the balloon idea, okay? It's actually the same exact thing, except we're not dealing with pressures, okay? Concentration is the amount of stuff, okay? Concentration C is the amount of stuff, and in this case here we're talking about reactants, so I'll just say amount of reactants per unit volume, okay? And usually the units are moles. We like to deal with moles per unit volume, liters, okay? We like to use liters there. Alright, so this is the equation for concentration, okay? Concentration equals the amount of reactants, it depends on what concentration we're talking about, but in this case here we're talking about an amount of a reactant, possibly, okay? So let's just say A plus B goes to C, some general equation. If I want to know the concentration of A, I'll express that like this, concentration of A. Sometimes this word here is really hard to spell out all the time, so to simplify it, they'll just do this in brackets. The brackets means concentration of A. Okay. And so if I want to calculate the concentration of A, I just need to get the moles and divide it by the volume. And the unit is usually a mole per liter. Okay. Now, when we increase the reactant concentration, in this case A and B, the rate also increases. Okay, so think about this. Let's just say you have a solution, an aqueous solution of A's and B's. This is a low concentration. Obviously, there's not that many A's and B's relative to this situation, where there's a bunch of A's and B's. Again, now you can't change the pressure of this because they're inside of water, okay? Because these are aqueous solutions, okay? So both of these are aqueous solutions. This is a high concentration, right? High concentration. And so again, the same idea applies just like in the pressure example. There's less space between reactant particles. This means that there are a higher frequency of collisions. Therefore, they're more likely to become C because the A's and B's are colliding so much more often. Okay, so increasing the reactant concentration increases the rate of reaction. So if you increase the concentration of reactants, increasing the concentration of reactants increases the rate of reaction. And if they say why, then you would just say, oh, there's less space between particles. All right? And then all of that means, I wrote that earlier, so there's less space between particles. We could comma, less space between particles. Reactant particles, okay? Reactant particles. And then of course this causes a higher frequency of collisions, okay? So this increases the frequency of collisions between reactant particles. And remember, collisions occur between reactants in order for them to become C particles or product particles. Alright? So this is the same explanation actually, okay? So let me write all these three down real quick. Alright, so the first one was increasing surface area. This only applies for solid reactants, okay? Because you cannot have a surface area of a gas particle, okay, or a molecule, okay? They don't have surface area, okay, because they're so small, okay? But a piece of metal like iron, that has surface area, okay? So solid reactants. If you increase the surface area of a solid reactant, the rate of reaction increases. Rate of reaction increases. Okay? And please, if you do explain this in words, you should not write an arrow, you should just write out increases. Alright? If you increase the pressure of gas reactants, okay, this is the balloon idea, right? Then the rate increases. Rate of reaction increases. And then finally, if you increase the concentration, okay, and usually when we're talking about the amount of stuff in a given volume, so in this case here in an aqueous volume, in a water volume, okay, concentration. So remember concentration, I'll just put in here, the moles per unit volume, okay? That's what concentration is, the amount of stuff in terms of moles in a given volume, usually liters here. So the amount mole over volume. If you increase the concentration, then the rate of reaction also increases. Okay? Now all of these are because if you do all of these, the reason is because the frequency of collisions increase. Frequency of collisions increase. Okay? Between reactant particles increase, right? And they have different reasons why, okay? Because, you know, if you increase the surface area, the surface sites increase. Okay? The surface sites of the reactant increases. You have more exposed surface for reactions to occur at. So we could just put here, I'll just put more surface sites, right? Let's say more surface sites. And then pressure, why? It's because there's less space between particles actually. And actually that's the same explanation for here too, when you increase the concentration. They're very similar, okay? So for both of these, concentration and pressure, they are because, you know, there's less space between reactant particles. Alright, so then these are the first three I'm talking about. 1, 2, 3. They have a very similar reason why the rate increases, okay? Alright, now the next two are a little bit more complicated, but it's not so bad. So the next one I will talk about is 4 is temperature. Temperature also causes the rate of reaction to increase. We'll talk about that. And 5, a catalyst also causes the rate of reaction to increase. increase, okay? So we're going to talk about these two now. Alright, so then first off is T. So number 4 is temperature. Alright, and this is true because, if you want to cook your food faster, you heat it up even more, right? So, and actually that's true. So increasing the temp, alright, it's temperature, increasing the temp increases the rate of reaction. Alright? And then we need to know why. So why? Just like we did earlier for the first 3. First off, when you heat up reactant particles, they move faster, actually. Okay, and if they move faster, the frequency of collisions increase because imagine particles going slow. Okay, it's harder for them to hit each other per unit time. All right, because it's just harder. Now, if they're moving fast, they're more likely, in terms of time, for them to collide. It should be intuitive, all right? You should be able to understand that. Okay, so when you heat them up, particles move faster. Reactant particles move faster. Okay, and so frequency of collisions increase. Okay, so this was frequency of collisions increase. Right? Now in addition to this, something else is happening. Because the particles are moving faster, they collide with more energy, okay? So they're more likely to become a product, okay? So when A reacts with B and they collide with each other, sometimes they collide with each other very weakly, and so they don't really turn into a C particle. They just bounce off of each other. Maybe because it's not a direct hit. Maybe they barely just skid off of each other. And so it's not hard enough or high enough energy for them to become a product. Okay, so another reason why temperature causes the rate of reaction to increase, it's 2. 1 here, the frequency of collisions increase because the reactant particles move faster. And then 2, the collision energy is higher. Collision energy is higher. Okay? In other words, they are smashing into each other a lot harder. Okay? Alright, so then there's going to be more chances for successful collisions. Okay? So this here means more chances for effective collisions. Just means that it actually can become product particles. More chances for effective collisions. This is opposed to particles barely skimming off of each other and not having enough energy to be a C particle, okay? Alright, so these are the 2 reasons why when you increase the temperature, the rate of reaction increases. 1, reactant particles move faster, so the frequency of collisions increase. There's more chances for effective collisions. And 2, also, the collision energy is higher, so then there's even more chances for effective collisions, okay? Alright. And the last one. Which is a catalyst, number 5. And actually, this list is pretty good. The 5 factors that affect the rate of reaction that I'm teaching right now. There's some more, but they're not as important. For example, like sunlight. You can use sunlight to cause a rate of reaction to increase. But we're not going to go into all those details, okay? Okay, so how a catalyst works is it'll take a reactant and help it become a product, okay? Alright, so before I talk about that, I do need to talk about a pathway, okay? So just like your sum reactant R here, okay? and you might take a path to get to your house. Okay, this is my example. This is your house. You can also take a more difficult route to get to your house, okay? In any case, when you get to your house, you become a product P, okay? And so now I'm just going to use R for reactant, becoming a product over time, okay? Reactant R becoming product P here. Now, if you take this path, you can get to your house a little bit easier. This path is a little bit more difficult, okay? It takes more time, right? And we're going to talk about how a rate of reaction occurs. If you use a catalyst, it's easier. Catalyst route. Okay? And if you don't use a catalyst, then it's this long route, okay? It's a little bit more difficult to get to the product. So it takes more time, right? And so these are called pathways. This is path 1. This is path 2. Right? And so there are different pathways. And so since we're talking about reactions, we need to talk about reaction pathway. And actually it gets really complicated. What it really means is when two reactants collide, so now I'm going to switch. This was just an example, right? So that we can understand what a pathway could be and how to visualize it. Really though, if you have two reactants, A, B goes to C, we don't really know, because it's beyond the scope of this course, but we don't know what happens when A and B collide. It's possible that when A and B collide, they need to somehow turn themselves into the right orientation, and then when they come close enough, they need to produce a tiny little particle first, and then that tiny little particle comes back into it somehow, some way, and then boom, it makes product C. A lot of things can happen, and so we don't learn the actual reaction pathway. They might call them reaction mechanisms, and we just call them reaction pathway. It's some reaction pathway. All right, so that's an example of how chemicals might have different reaction pathways. We're going to do the simple first. The first reaction pathway is, assume we have, to get a good visualization, assume we have this particle, right? And this particle, when it comes into contact with this piece here, what happens is this piece here fits onto this particle. Alright, so this is the catalyst. Actually, we'll do it without the catalyst first. This particle here becomes two particles, okay? And alright, so the particle breaks up into two, okay? So that's like a reaction, okay? And this happens, but it's very slow, okay? When you add a catalyst, so we're going to assume this is my catalyst, okay? What happens is that catalyst can fit onto this particle and then break it up into two, okay? So let's do this in 2 steps so you can see what happens. Alright, you see how that thing fits right on there? And then it breaks it up into 2. Alright, so notice that the reactant, we'll call this R, reactant. Now it's into 2, so it's products now, right? Products, because it's not R anymore. But the catalyst, check out you know that this is a catalyst, I'll just say cat for here. The catalyst does not get used up, okay? It's still around. The reactant gets used up, alright? The first step, the catalyst attaches onto the reactant particle. It helps the reactant particle split up into 2. The reactant gets used up, is no longer there, however the catalyst remains. And if there's a lot of R's, then this catalyst can continue going to catalyze those R's to break them up to more P's, if there are more R's, okay? And so up here, this would have been the product and this would have been the reactants. Alright, so this is one reaction pathway up here. So we can call this reaction pathway 1. And this is another different reaction pathway because it involves a catalyst. Reaction pathway 2. The reaction pathway 2 allows the reaction to happen faster because when this catalyst attaches onto it, it somehow allows the reactant to be more easily react. In other words, it lowers the collision energy, okay, for an effective collision to occur, okay? So lowers collision energy, to, actually let's just say lowers effective collision energy, that's probably better, lowers effective collision energy. Okay, and this effective collision energy, we can call that the activation energy, okay? That activation energy. Okay, so the activation energy is the energy required for particles to collide to become products, okay? So this reactant particle actually, it's just colliding with itself until it finally breaks apart into a half, right? So, oh, this is R, sorry, R and these are P's. Sorry about that. Reactant becomes two product particles. Reactant adds to the catalyst attaches to it, and then catalyst comes off, and then two product particles are formed. Okay, so this activation energy is the energy needed for reactant particle to become two P's, okay? And that's what how a catalyst works. It lowers the effective collision energy, or it lowers the activation energy, all right, by changing the reaction pathway, okay? By changing the reaction pathway. Again, the activation energy is the energy required for an effective collision. Because remember, some collisions are not effective. They just collide and nothing happens. Some of them are collide a little bit harder and then they can become products. Alright, so then that's the catalyst. And that'll end it for the rate of reactions. Remember, 5 factors affect the rate of reaction. Pressure of gas reactants, surface area of solid reactants, concentration, okay, also affects the rate of reaction. Temperature affects the rate of reaction, and catalyst chain affects the rate of reaction. And you should also know that the first 3 is their frequency of the frequency of collisions increase, and the next 2, which is the temperature and catalyst. Temperature, there are 2 reasons. Temperature is because the frequency of collisions increase because the particles are moving faster, because you increase the temperature, and then also because the collision energy, when they collide with each other, with more energy, so then they have more chances to be effective collisions. And then of course the catalyst, you change the reaction pathway, one with a lower activation energy, okay? And then of course, yeah, that's it.